All right, that did it. So quickly, I didn't look at chat, but quickly, and I will ask this on the test. This is worth thinking about. If you first start out with the derivative, which of course is speed, of course the derivative of cosine is negative sine times the derivative of 2t, which is 2. So hopefully you got this for the derivative. And so of course that's the formula for the slope at any time. Not so much the slope, but the speed. So if I go in there and stick in 3, I could write that as a decimal or exactly. I think I'll just write it exact in the interest of time, since we have wasted so much of our precious time. So whatever that numerical answer is, that should match the vector. And we'll go look at this in just a second. That should match what we saw on the graph. So that's the velocity answer to this, which is actually a vector. And then if you Pythagorean theorem that mess, maybe you put this in the chat already, but I'm going to figure out what negative 6 sine of 6 is so that I can square it. And I'm going to add that to 6 squared, which is 36, plus 3 squared, which is 9. If I take the square root of that, the square root of what's roughly 47, you should get like 6.9. So the speed I didn't put any units on any of this, but we'll say meters per second. So I could go back up here and write meters, and then that would make sense. And over here, I would have to say time in seconds or something of that nature to make that a reality. For you future physics people, that's the difference between speed and velocity. Speed doesn't have a direction. Speed's just a number that says how fast you're going, which of course makes sense. Most of the time, if you're asked how fast you're going, you're only answering that as a speed. Just because you don't care where you're going, but of course you can appreciate that does make a difference. And then of course arc length is the same thing. You're taking the derivative of everything, but you are taking the integral of that derivative, and each of the parts of that derivative are squared. And this is a formula. My formula, I won't pull my formula sheet up, but my formula sheet shows this. This isn't something you need to memorize. But we're going to need to take that integral. And of course, that's going to be horrendous to take. So we aren't going to be able to take it. If you stick that in your graphing calculator, I have everything already typed in for this while I was wasting away time. So if I graph that, so on the test, I will certainly say evaluate this with the calculator or whatever. So I don't know if you graphed this already, but you get kind of a really crazy fun graph for this thing. It's kind of a, I don't know, Halloween looking tooth sort of deal, which I assume you did. So if I say second calculate, find the area under that curve from 0 to 5, I get the approximate answer, which I get 37.148. And of course, in this case, if you were going to be accurate about it, speed is arc length is a length, as it says. And so the answer to this would be in meters. Won't take the time to talk about this, but I wonder if you could actually see the units there if you put them in. You're squaring something. I mean, does it make sense that this up here is a meter because that's a length, but then down there you're squaring it, but then you're taking the square root of it, but then you're multiplying it by dt. A little dt is a little bit of time. I wonder if you could actually get the units to kind of work themselves out to be meters, even if you didn't just kind of write it there like I did based on common sense. But that's always a good thing to do. So are you happy with that? I mean, I'm speaking about it as though it's obvious and easy. Even the math isn't hard, but from yesterday, anything you want to ask about that? Do you feel good about that?
Yeah. Isn't the in 2D the arc-like formula have like a square root of 1 plus something?
Say that one more time.
In the
Oh yeah.
in 2D, yeah.
Nice job. Good memory.
I'm just wondering where that went.
Good job. I'll just
I
quickly
think we
tell you this. I stopped here yesterday when we talked about the fact that that little tiny arc length, since this is a little bit of X and this is a little bit of Y, and that was the statement I wrote yesterday. But in 2D, we said, I don't really know what to do with that. You know, what is a little bit of X? And so we said, well, why don't we go in here and we'll divide everything by dx squared. And of course, that's okay to do if you multiply everything by dx squared. But if there was a dx squared inside the radical sign, then I could take it out as a dx. So algebraically, do you understand that I didn't change anything just now?
Yeah.
And so notice this is 1. And so then we say, oh, okay, our 2D formula for this is actually 1 plus dy over dx. Oh, I know what to do with that now. You say that's a derivative. And so I'll take the derivative and square it. And that's the integral I'll take. That was actually our 2D formula for this. So that's why the 1 was there.
Okay.
Love it. Good question. And so in our case, the fact that, let's see how easy is this for me to pull up. Let me check really quick. In our case, because we can take the derivative of x with respect to t, because it's a parametric equation defined by something totally different. We're basically saying, okay, I have a dx sitting there, a little bit of x. Well, then I'll just divide by dt squared. And so it's actually missing on here. There really should be a, whoa, what was that doing there? There really should be a, what are you doing there? Cut, crop, cut. There we go. There really should be a dt out here. So in the end, I took dx squared, I divided by dt squared. So now I have dx dt divided by, or dx dt squared, and then the dt that I have to multiply by to kind of fix the fact that I divided by dt squared kind of pops out. I'm sure I'm saying that too fast, but
yeah, no, that makes sense.
That's a wonderful question. So, you know, again, keep an eye on this note sheet, just because this is what you're going to want to be able to stare at for the test. So, and again, you know, the point of this particular section is to, you know, be able to find the speed and the velocity and the arc length, not to, you know, for me to give you some hard equation. Obviously, I could give you a hard equation right here from Calc 1. The derivative was hard to take, you know, natural logarithm of cosine cubed or something, and you know, make it really hard. But I want to make sure the derivative is fairly easy. I want to ask you a question. I won't, oh man. I think you can still hear me. I want to ask you a question I won't ask on the test, which is, what's the maximum speed? I guess I'm curious to know if you agree that that's an interesting question. Can you guys hear me, by the way? Like,
yeah.
Oh, good. Zoom just went black again, so I'm hoping it'll not do what it did last time. But I want you to think about that for a second. How would you find the maximum speed? Because of course, the fun part of this, and I may go do this, let's see. The fun part of this is not just to say, you know, what's the speed of the Falcon at 3 seconds, but what about, you know, 1 second and 2 seconds and 3 seconds, and 4 seconds and all the other times. So it's actually changing speeds constantly, which of course is a wonderful thing in the real world, to think that, you know, you could do that. You could actually change speeds. But then, and this is one of the great takeaways of what calculus is, well, I wonder what the fastest it was going in that. So again, I want to, you know, highlight, I'm showing you this because it's cool. It's a wonderful question. If we had lots of time, you know, I'd make a project out of this and, you know, we'd really go to town with it. But I just think it's fun to think about. So what are your thoughts? Like, how do we find the maximum of something?
Well, in the past, that was where the derivative was equal to 0 where it peaked?
Yeah, Cheyenne is right. And that's also going the right direction here. So that formula gave us every speed, right? Or velocity. So how do I get the maximum of something? Well, the maximum is when there's no change, right? Now think about speed. If you're speeding up, doesn't that mean you have an acceleration? So if you're not accelerating, now think about it. If you are accelerating, that means you're going faster and faster and faster, which means you haven't reached your maximum speed yet, right? But then if you actually reach your maximum speed, then you're no longer accelerating. And then presumably, then you would start decelerating and you go down. And so does it make sense? It's actually no different. Given that if I reread it this way, because this is also true, I could say this is your velocity now. Well, what's your acceleration? You punch that out. Ben put in the chat directly to me that he got a different answer for arc length, by the way. So I'm thinking about that. I don't see any mistakes in what I did, though.
Yeah, I'm not sure why I got something different. It's kind of weird. I thought I put in the same thing you put in, but.
Oh, it could be radians and degrees.
Oh yeah, that's probably what it is, because I think mine might be.
I'm in
Might be
radians, and that's what you
degree
should
mode.
be in
Okay,
here,
I-
although I guess there's
yeah.
nothing saying that that's the case.
So when you're putting that into your calculator, you should be in radian mode.
Yeah, and I don't mean that to be a trick question. Anytime sine's involved, sine or cosine's involved, that's a consideration. And I don't think that's obvious, but at this level of math, the default is radians. It's only kind of if you're looking at something geometrically and there's degrees are listed in it, then. But that's something like on a test I would hopefully catch, and that's a problem in this class because occasionally we are going back and forth, so you could easily be in the wrong mode, or but that if Bennett answered that 30 or whatever he got, and I had the sense to go check and see he has it written down correctly, how did he get 30 and I got 37, and I went to degrees and you got the same answer, I would have just said good job. Probably wouldn't even have said anything, probably wouldn't even corrected it.
Cool.
Yeah, I'm getting the same answer now. So.
Sweet. So I'm looking for that. That's what we did to find the maximum before. We took the derivative and set it equal to 0, right? So that's kind of cool. Well, in this case, that actually means something. In other words, you're not just taking the derivative and set it equal to 0. When you take the derivative, you're talking about the rate of change of something, and the rate of change of velocity is acceleration. So this has a name. And of course, the derivative of sine of junk is cosine of junk, but then we multiply by the junk, the derivative of the junk. And so that 6 turns into a 12. And the 2t just goes to 2, and the 3 actually goes away. Be very easy, I think, to think a 3 was there, but that goes away. So how do we set that equal to 0? Well, notice I said maximum speed, not maximum velocity. So isn't the speed, as we said before, the integral of all that junk squared? maybe I'll just square 12. Since it's negative, I'll just square it myself. And then I can write it as this. Now, interesting question. What is this being evaluated from? From what to what?
Wouldn't it be 0 to 5?
0 to 5 would give us our, wait a second, speed. We did arc length. Wait, this isn't an integral, you should say. That's what we did for arc length. But speed was just the Pythagorean theorem, right? So isn't that the speed?
Real quick, for my v of t, I had just t as the z component.
Did I blow it back there? 2t. There.
Okay, yeah, I might have written it down wrong then.
Yeah, the original one was t squared and then 3t. So I don't see any mistakes that I made, although that would be weird, as you know. Now, in a sense, that's not really the speed. That's the acceleration. So I can't really say that's the speed. I'm interested in, that's actually, you know, the magnitude of the acceleration. I'm interested in when this is equal to 0, like solve for t. What value for t makes that equal to 0? Because the maximum speed is when the numerical value for acceleration, and maybe we'll get a chance to talk about this with curvature, but acceleration is a vector. In other words, it's telling you what direction you're accelerating in. And if I do the Pythagorean theorem on it, then I'm actually getting kind of the scalar acceleration. So that's really what this is. This is the scalar value for the acceleration. And so if you're not accelerating, that would be one of your maximums. Well, it could also be your minimum, isn't that right? So let's see if we can solve this. Well, fortunately, I can square both sides, and that takes care of the square root, which is very good. And let's see.
Are we
Then-
finding when the max speed was or what the max speed was?
Ultimately, if I'm understanding your question right, ultimately, this is going to give me the time at which the maximum speed occurs. We don't know what the maximum
Okay.
speed is, but it'll give us the time when that happens.
And then you just plugged it to, okay, I see.
Nice job. So then if I subtract 4 and I divide by 144, I get that number. And then if I square root, uh-oh, there's a problem. If I square root both sides, then I'm square rooting a negative. So that feels not good. Let's see, absolute values. You'll see a number of absolute values in this section because you know, negative is really just directional. So I'm wondering, you know, can I take the absolute value of this and sort of proceed as though it was 4 over 144, or is that not okay to do? Not sure. Thinking about that. Let's proceed with that and just see what happens. It's the whole fun of math. So that may not be okay, but let's figure it out anyway. So I'll make a note to us here. Absolute value. Can we do that? Should we do that? Is it possible to do that? I don't know. If it is, then we'd say we have now the cosine of 2t. If I square root both sides, fortunately, I can square root 4 and I can square root 144. So I get 1/6. So now I have the inverse cosine of 1/6. Second cosine of 1/6. And I get 1.4 approximately. So I get 2t is approximately equal to 1.4. So t would be approximately 0.7. So first, we're sort of curious, like, okay, what is that? I mean, is that a right answer? Because remember, we took the absolute value and so forth, so we're not really comfortable that was even possible. But let's just go out of curiosity. Let's go to the graph and see what we find out. Of course, one of the fun things to do here would just be because remember, you don't need calculus for calculus. If you just take that expression right there for speed and you just plug in values for, t, I mean, you'd have to, square root it and so forth. But let's just go to, I'll stop that share for a second. Let's just go over to even a simpler version. Looks like we lost our glorious. But I don't even have to graph this. Isn't this an expression for our speed? Gosh, what is this doing this? So I'm just going to say the constant value A, let me type or not. Six sine of 2t. Maybe I'll do this on my iPad since something's just freaking out with Zoom today. I don't not know what's going on. So what I'd like to do is just answer this without calculus, because again, one of my largest concerns is just whether you leave this class being able to think, as opposed to just having sort of formulaic approaches to everything you do. So I'm trying to type and it's not letting me type. So I'm going back over here. Let's go to this version. So would you agree this is the speed? So I'm going to say, see if this makes sense to you. So we have our value for t, and I'm going to say t is equal to 1 for right now. And so isn't this our speed? If I say, can I say s for speed is going to try to make this a vector? I'm not sure. Let's just find out. So isn't the speed this? If I take the square root of, well, what was our speed? It was -6 sine of 2t, right? Put my phone to make sure I don't blow this. -6 sine of 2t, and that's squared. So I got parentheses started. So -6 sine function sine parentheses is in there, 2. And then I need the value for t. And then I need to close that parenthesis and then close it again and square it. And then it gets a little easier. Plus 2t squared, which will really be 4t squared, save a little bit of time. And then plus 3 squared, which was 9. So that's kind of cool. This is what Desmos would do, right? So it's telling me at 1, my speed is 6.54. Just to check our work from a minute ago, I could go back up here and type 3 in. But what I'd like to do that's kind of fun here is I'm going to go in and change the settings so that our It looks like our increment is 0.1. So this is actually going to go really slow. So if I turn this on, I'm going to set this back to, well, I'd like to start at 0. So I'll just start close to 0. I just want you to watch those speeds. Did you see how it just got up to 8 there a second ago? Now it's going way too fast. But what did we just say mathematically? I thought I had that set to 0.1, but settings, increment, it says right there 0.1. Why isn't it acting like 0.1? Increment 0.1. Da, 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 da. Can't see it. Maybe this app just doesn't let me have the same control. So let's see, what did we just say? We said that the maximum occurred, it was at 0.7. So the question is, if I get around 0.7, does that appear to be a maximum? .78. So let's go a little past 0.7, like say to 0.7, I don't know, 5. The question is, does it get less? Notice it didn't, wasn't it 6.78, just got bigger. So it doesn't look like 0.7 is a maximum, does it? Looks like something's wrong. So that means that absolute value business, maybe that wasn't okay to do. What's this? Square it, subtract 4, divide by 144. Take the square root. So perhaps no is the answer to this, since that did not seem to work. We have brilliant ideas. Just double checking stuff that I typed in. And you know, the thing that should bother you about this is if I come over here and, you know, change this to other numbers, I certainly am getting different answers to this.
Is it possible that there's no maximum for the speed in this case?
Really, that's the thing that's bothering me is there certainly is a value for maximum speed. So I'm going to open up the I can't remember when I made this before class, but I can't remember if I actually had. Yeah, fortunately, it's already in here. Excuse me. So this V here is kind of our speed. Again, not our velocity because it's a vector, or not a vector anymore, but notice it's 7.1. And so if I say, again, I got to slow that down, which it seems like I can do here. So you're looking at this number right here, 10 point something. Excuse me. Unfortunately, I played with this a little bit yesterday and had wonderful success with kind of a sample problem I made. And I thought, oh, let's do that with the Falcon problem. And you know, it's not working as good, but do you see how it just paused right there? Did you see that? It paused at Watch how it's growing, 6.7, 6.8. See how it just paused at 6.89 and then it just went back down again? That was a maximum we should have been able to find right there. And then it's about to do it again. Watch it again. See how it's getting right up to, see how it just got to like 8.24 and then it went back down again. So it has maximums, more than one. And it's kind of cool about it is there's relative maximums. Notice this is the biggest one right around here. Let's watch it, 10.41, 42, and then see how it started going back down again. Isn't that interesting? One of the things I want to show you that I think is kind of amazing that I discovered about this yesterday just by playing is these maximums actually occur. Looking at this from the air, it's a little bit easier to see it, but it occurs right here. Keep in mind what you're really looking for is the longest green arrow you can possibly get. You understand that? The longest green arrow is what produces this, and those happen, if you will, on the straightaways. So looking at it from the air, if I back up just a little bit right here, so see how the arrow is getting smaller? Watch how when it gets right here, right in the middle of this, that's when this velocity actually maxes out. So it's getting longer, longer, longer. Let's see what it maxes out at. I forgot which one this one was, but 8.24. That's where it maxed out, right around 8.24. It's not super. So there's actually going to be a maximum right here, a maximum right here, and a maximum right over here. In algebra, you probably remember those are called the inflection points, and inflection points are found when you take the second derivative and set it equal to 0, and that's exactly what we're doing. I can't reconcile why we're getting a negative number for this and why the math kind of isn't working out to show us that, but it definitely has maximums. That's kind of the issue here. So I won't do it now just because it's going to take too much class time, but I want to cheat. I want to play around with this and try to figure out, like I can cheat and find the maximum velocities and what times those are at least approximations. And, then maybe we could reverse engineer and sort of figure out what is going on algebraically. It could be the only thing I would say about this if you find yourself wanting to think about it as well. But do you remember there's lots of answers to this? Anytime you take inverse cosine of something, there's a lot of answers to that. So, and you have to hunt for them right here. So 1.4 would be here. Do you agree with that? Because remember 1.57. Great, you're not seeing that, are you? Are you seeing a unit circle yet, or is this kind of playing the freeze game?
It's stuck on your note sheet.
Gosh, this has been a frustrating day for technology. I'm really sorry about that, my friends. Okay. So 1.4 on the unit circle would be right here, since this is 1.57. And since we're talking about cosine, the cosine of an angle, cosine is the next coordinate, then the other one would be right down there at what we would call, I guess, negative 1.4. So if I kind of add 2 pi to that, then I could rewrite it as 4.88. So at least logically, just because it's kind of cool to understand this, if I take 4.88 and I add another 2 pi to this, then would you agree that this is also an acceptable name for this, 11.16? And I could do the same thing with 1.4. If I take 1.4 and I add 2 pi to it, I also get another name for this, which is, I'll write an equal sign here, 7.68. So again, this doesn't seem to be working just because that didn't match what we saw in the graph. 0.7, the time of 0.7 was not one of the correct times. But remember, this is equal to 2t, and so I'd have to divide every one of those by 2. So I should get t is 0.7. And then if I take 7.68 and I also divide it by 2, that's 3.84. And then for the ones down on the bottom, if I divide 4.88 by 2, I get 2.44. If I divide 11.16 by 2, I get 5.58. So the point is, there's lots of answers to these, right? And we just saw on that graph, there was a number of maximums. They were relative maximums. One of them was the ultimate maximum. It seemed like it happened further out, right? When that longest straightaway at the sort of the end of the 5-second flight that we looked at. But every one of these would represent a maximum of sorts. And that's what we're seeing over there. I just can't sort of see what about this math isn't working. Now it is possible that the 0.7 is kind of a negative one, and maybe some of these other ones work, but I don't know. I can't get to the bottom of that. I can't figure out what's going on there. So I'll probably say something about that tomorrow. Another interesting thing. Let's see. We probably don't have to do that. Let's do. Let's do a. Let's do kind of a canned question that actually comes out kind of neat, but it's related, and this is what made me think of that kind of Falcon problem idea. But I saw a question in your textbook that talked about an eagle rising on a helical. What's a helix? And this is actually practical for quite a number of reasons, but a helix is kind of like the threads of a screw. It's kind of going up like that. DNA is kind of based off of that. I'm told that if airplanes, like getting near an airport, need to drop elevation or gain elevation without, moving across the country, that's what they do. They'll kind of circle and work their way down, or circle and work their way up. So it's kind of interesting that the book made this kind of a bird doing this. But this is kind of cool. What if it was rising at 100 feet per, we'll say, minute, because it wouldn't be a second. And let's say that this helical path was on a 250-foot radius. So that certainly creates what we've been discussing, which is a 3-dimensional path up in space. And so the cool thing is looked at from the air, what would you see if we were looking down at this from the XY axis? What would you see of that helical path if it was rising helically, that's a word, on a 250-foot radius?
Just a circle.
Yeah, that's exactly right. You just see a circle. And it would be hitting at 250 in both of these cases. And so this is a rare problem in the sense that you actually would have a shot at creating this equation for yourself. Like I don't have, like last time I just made up this random bunch of functions. The first was a cosine, the second was a problem, the third was a line. each different functions for the X, Y, and Z of the falcon as it flew, and it made a really cool pattern. But this time it's actually a circle, except that it's rising. And so you actually could write this yourself. I mean, do you know that this circle right here would be the same thing as, well, not quite this. If I said cosine squared plus sine squared equals 1, why would this be different? Like that was a circle, right? Or that's the identity for trig, but it's also the equation of a circle, except for that's a circle of radius 1. And so all we'd have to do is modify that by putting 250 squared over there. Isn't that true? Then that would be correct. So for that reason, this would be your function. The x coordinate would be 250 times the cosine of t. The y coordinate would be 250 times the sine of t. That would actually take care of the circle in polar mode. And then we just don't want it to be flat. Like we don't want it to stay there. So we don't want z to be 0. If z was 0, then it would just be flying around in a circle. What would it be flying? It'd be walking in a circle on the ground. But this is where you'd put 100. And it's 100 feet per minute. So that's actually got a t in it. So if t is 1, then it'd be 100 feet. If t is 2, that'd be 200 feet. So it's rising at a rate. So if I take that rate up there, 200 feet per minute, and I multiply it by a time that's in minutes, then I'm going to get an answer in feet. So that's kind of why I'm throwing that, or why you would need to throw that t in there. So this would actually be the path that the eagle was taking. Now I don't think we need to do, I don't think we need to do this again, come up with speed and arc length and all of that. But of course, that's kind of a cool question. If you let it fly for say 6 minutes and wanted to know how far it had flown. I mean, that's of course interesting if this is an airplane. These are super interesting questions. But again, I just want to ask you another playful, kind of an interesting question about this, which is this. What's the, you don't need to know this. This isn't like a test question, and it's not on your homework. This is just an interesting question. But what would the angle, this is a little bit from yesterday, what would the angle it took off? This is very poor grammar. How do you say that correctly? The angle it took off at. You're not supposed to end with a preposition at. So I want you to think about that for a second, and then we'll do it. Well, remember yesterday, just for the fun of it, we said that the actual slope, was actually found by taking the derivative of z divided by the square root of the derivatives at x and y, except you Pythagorean theorem those two. Again, I won't go back over why we said that was, but ultimately z of t is the height, and in the XY plane, the Pythagorean theorem of X and Y are actually producing the run. So we said yesterday that, at least conceptually, that this was the rise and this was the run. And so this was how we're going to get the slope. So I would like to see if you could do that. Now, in our particular problem at takeoff, if I say it, the angle it took off at, what does that information imply? What do you know? Because I said we're interested in when it took off.
Time equals 0.
Time equals 0. So can you find the slope? Can you find the slope that the bird took off at based on this? So 250 cosine of t, 250 sine of t, 100 t. I'm going to go graph this just for the fun of it while you're trying to calc that. So I let this go from t equals 0 to 6 pi, which is around 12 minutes, if you will. So that's going to create 3 laps. So sure enough, it really does look like a circle from the air, but it's climbing. So of course, this is the shape of a spring. It's kind of a cool, kind of a applicable, particularly applicable path through space, if you will. So you should say, great, I can take the derivative of the z coordinate, that's 100. The derivative of, notice there's no t in it anymore. So there's no place to plug t in, so it's just 100. Whereas the derivative of 250 cosine of t is negative 250 sine of t. And I'm going to be putting 0 into that, and the sine of 0 is 0, so that's going to contribute nothing. So 0 squared. The derivative of sine is cosine, so the derivative of 250 sine would be 250 cosine. When I put 0 in that, I actually get cosine of 0 is 1, and I get 250. So I end up with really 1 over the square root of 250 squared, or just 100 over 250. And I guess that'd be 10 over 25, or 2 over 5. All right, 2 over 5. So again, this is kind of neat. If you stare at this, does that look reasonable? If I go down here to the ground, and notice it's very difficult to, I won't take the time to draw the vectors in for this, but I think I could, I mean, I can copy this in a second, but if you kind of lay it down even with the ground, does that clearly look like, less than 45 degrees, for instance? Doesn't that look like about 2/5? So it's pretty reasonable, doesn't it? That's kind of cool that works. What do you have to do? You should already know this from before, but again, these are just good conceptual understanding questions, but I didn't ask for the slope, I asked for the angle. What do you got to do? You should know this from the projects we did and so forth. And even if you forgot, you should be able to say, well, I'm interested in the angle here. If the rise is 2 and the run is 5, that implies a right triangle. So if you draw that, you should say, oh, it's tangent. And I mentioned before, either last term or before, but you think of tangent as living in trig class, like sine, cosine, and tangent, and then all of a sudden here we're using tangent in calculus. Well, that's why this word is in calculus, because tangent, the tangent to a curve is the line that represents the slope of the curve. And when you take 2 and 5, you're going to be using tangent. So I actually don't know which one came first. Was it the name on calculus and then it got applied to the name in trig, or was it named in trig as tangent and then somebody said, well, it's the same thing, let's call that a tangent line in calculus? So which came first? Notice in this case, a person would probably want to be in degree mode. Does that make sense? If you answer this in radians, this is an example of one of the problems we have in this class, because I find myself thinking, I don't want to hear the answer to this in radians because I'm not going to be able to visualize it. I don't kind of think that way. So I'm going to degrees for this. As long as you label it, doesn't make any difference. So I say second tangent of 2 divided by 5, and I get like 21.8 degrees. Again, all I'm really trying to do today is just kind of play around and answer the interesting questions. In this case, in this particular example, because the bird is rising at a constant rate, I think the slope the entire time is probably 21.8 degrees. Does that make sense? In other words, it's like a 20, if I think of it as an airplane, it's like climbing at a 21% or 21 degree angle, 22 degree angle the entire time. That's kind of cool to think about. I think I will show you, just because this is kind of interesting. This is, and one of the reasons this isn't a textbook is watch what happens if I ask and answer this fairly straightforward and interesting question. Again, I think you're already good at this, but what if we did ask about the speed of this? So you know that the speed is first found by taking the derivative of the position. So that gives us velocity vector. So we said the derivative of 250 cosine was negative 250 sine. The derivative of 250 sine was 250 cosine. And the derivative of 100t is 100. So there's our velocity vector. We say, okay, that's pretty easy. That makes sense. If I move on then to the speed as a function of t, then you say, okay, great. Well, then that means you've got to square those and kind of Pythagorean theorem them. But I want you to stare at what happens if you do that. This is just kind of a fun example because we've kind of admitted defeat with these questions every time. And just kind of, stuck it in our calculator at 3 seconds, or, whatever the person happened to want to know. But if you don't give up with that, do you notice some beauty here? Because you end up with 250 getting squared, which is of course a big number. 662,500. Notice the square takes away the negative sign. I never wrote the squared on 100, but I'm adding it now because I see that I forgot it. In terms of your trig knowledge, what's really neat about this particular expression right here, though?
Something turns into 1.
Nice job. If you factor 6,200, 62,500 out, 62,500 out of both of those, you end up with sine squared plus cosine squared equals 1. So this actually becomes, I guess you would say, square root of 72,500. So as a point of interest, if I'd said I want to know what the speed of this thing is at not any old time, but say 3 seconds again, most of you, probably myself included, would have probably got it to here, and then we would have just plugged in 3, and we would have got, some kind of a decimal answer and written it down. But based on what I just did, what's going to happen if I, ask you a second question and ask you for 4?
It's going to be the same exact speed.
Yeah, notice there's no t in our formula, like the t dropped out of it as a result of just an interesting question. The t dropped out of it, which means this is the speed always. That's the speed entirely consistently. Now, and this is the thing, I might say a couple of things about this tomorrow, but I want you to be able to finish this class, and so I'm going to kind of let you guys decide. And I want you to be able to focus on the test. I want to spend tomorrow reviewing for the test, and then we'll take the test on Thursday and be done. But do you
Cool.
notice what's interesting about this path right here? Does it make sense? This path is really consistent. In other words, it's just kind of like, does it make sense? The eagle, in a sense, set the angle of its wings a little sideways so it would actually curve, but then it just kind of stayed there. It's kind of making the exact same left-hand turn as it flies all the way, and there's no switching. The Falcon was like, I'm going to go left, I'm going to go right. It moved around a lot, and as a result of that, the speed of the Falcon was actually always changing. Well, notice this is entirely consistent in terms of the way the shape works. It has the same, well, the thing we're maybe not have time for is curvature. The next section, so cool, I want to teach it to you. This has the same curvature the entire time. So what I'd love you to leave with today, kind of conceptually, is kind of that basic idea. If I have a path that kind of looks like this, super sharp, and just some kind of crazy path, and again, I'm drawing this in 2 dimensions just because, so that you can at least see it. But if it's a smooth curve like this, that's going to cause changes in speed. Whereas our helix didn't cause changes of speed. And we actually saw, oddly, that the maximums are actually kind of in these straightaways. This one would have a whole bunch of maximums kind of right in there, maybe. It's kind of at those inflection points. Those are all the maximum speeds, because that's where those velocity vectors would be the longest. And we're going to Pythagorean theorem those velocity vectors. And so that's why. Any other place, they're actually fairly short. So coming out of this turn, if you will, that vector might be pretty short, but as it turns here, it's going to get longer. It's not very tangent. And then when it gets here, it's kind of going to be its longest. So that's why the maximums are at those points. And we should be able to take the derivative of the velocity vector and get acceleration, set it equal to 0, and actually find all those points. So that's really cool. And in 14.5, which I'll mention tomorrow if you want, but this is kind of like maximum curvature right here. Because that's a really sharp corner, if you will. And I guess I'll say this kind of going out the door, but I'm saying this because you might take physics later on, or I teach this in dynamics too, in engineering for those of you that are taking it. But if you're kind of right here, that's your velocity. It'll be tangent to the curve. That'll be your velocity. But there'll also be another arrow in the same location, and that's what's called tangential acceleration, which is actually just a speed change. So that's, if you're driving a car, that's pushing on the accelerator, like, oh, I think I'll go faster. So that's a vector too. Didn't we see that when we took the derivative a minute ago of velocity, we got an acceleration vector? So it's pointing somewhere. So that is tangential acceleration, and that's a speed change, and it's going the same direction as you're going. So imagine yourself driving around a corner in a car. You could be on cruise control as you go around the corner, which means the acceleration tangent is nothing. You're not changing speed. Or you could actually be braking as you go around the corner, which would actually mean the vector would be going backwards because you're slowing your speed down. Or you could be pushing the accelerator and speeding up as you go around the corner. But there's actually a second component to it in this, and that's called normal acceleration. Normal means perpendicular, so these are 90 degrees to each other. And this is actually a direction change. So acceleration actually has two components to it. And it's actually that direction change that's actually causing you to kind of cruise around the corner. That's what's causing you to turn right. And that thing will be pointing kind of toward the middle of the circular path that you're on. And it turns out that if I was to kind of move that acceleration normal vector over here so that they're head to tail, then it's actually this vector. That's actually the acceleration vector that we just got a minute ago. In other words, when I take the derivative of velocity and I just get some random vector, that's where it would be pointing. So you break it into its tangential and normal components, because the tangential version is what changes your speed and the normal version is what changes your direction of travel. So it's kind of a cool concept. And so you can see, at least conceptually, that this is all related to curvature. I mean, that's the longer the AN vector is, then that would make kind of a tight turn over here. That would have a really long AN vector because you're really turning super sharp. Whereas if you're kind of casually turning or barely turning at all, then you're not going to have a very long acceleration normal vector. That's kind of the idea.
I'm gonna get into an accident thinking about this while I'm driving.
Say it again. Say that again.
I'm gonna get in an accident thinking about all this while I'm driving.
No kidding. It's really neat stuff. But it's just the cool takeaway from all of this is just how much there is to think about when you actually get 3D motion involved. And it's even more interesting in the sense of kind of a bird, because if a bird wants to turn, think of an airplane. If an airplane wants to turn, they don't just turn, right? What do? They actually bank, which is called torsion. You actually bank to cause that turn to happen, if that makes sense. And so following a path that, I just drew a two-dimensional drawing right now, but if you're actually following a path that's in space, there's even more to it than this. And that's what I wish we had time to talk about. But you're turning at an angle, you're torsioning, if you will, you're changing the axis so that you're making a turn. And so it's just amazing what 3D adds to all of this. You already saw, a hint of that so far in what we've done, but that's, I don't know, at least kind of opens the door to kind of the beauty of all of this. So let's just, because we can, take a quick look at I just want to make sure that, and some of you already did this yesterday, so good on you. But I just want to make sure you look at the assignment for today and think, oh yeah, that's easy. I can do that, no problem. Because there's only a few questions in it.
That was
So-
originally due last week, right?
Yeah, and I fixed that because it's due, basically it's due Wednesday night because I want you to have it done before the test. But there's only 5 questions in it. So, and this will, this will be the flavor of the test as well. If I come up with a curve, and when you see, R of t, I want you to see that as a position because R is a radius. And so this is a position curve. But notice it just says find the length of it. So do you find yourself saying, okay, we did some of that. We did some of that yesterday. We did some of that today. Notice when you find the length, that is an integral problem. Therefore, you have to say what t is. And notice in this case, t is kind of apparently not timed because it goes from -6 to 4, whereas this one, it goes from 1 to 3. So those aren't terrible. But notice every one of these questions is the same question in the sense that it is asking for you to take the derivative because you need the derivative for the length of the curve and you also need the derivative for the speed of the curve. Notice because of the word speed though, and that's the only thing I really taught you that was kind of new today that you actually needed to know for this assignment is that's a numerical answer. That's a scalar. It's not a vector because it said speed, not velocity. Hopefully they didn't screw that up. Let's check. Yeah, so they're giving a numerical answer to that. And then just another length of the curve question. What about this last one though? Does it explain itself enough that you could get it right without me saying anything? Because this is actually an introductory idea to the next section 14.5 that I was just hinting at a little bit today about all these planes that kind of describe the direction you're going. The unit tangent vector. So I was just going to find the tangent vector. And as we talked about today, well, that's easy. I just take the derivative of all these parts, right? And I just put them in here. Great. Except for this didn't say the tangent vector or the velocity vector. It could have said velocity. But notice in this case, this is not applications. They're not thinking of this as, the path of a falcon flying through the air or something. So they said tangent vector, not velocity, because they're just saying this is just some curve. So find a tangent on it. Same process. I'm going to take the derivative, but they said unit. What do you got to do? What do you got to do if it's a unit tangent vector?
You have to divide it by the magnitude.
Yeah, you got to divide each of the terms by the magnitude. And notice that for that reason, you can't know the magnitude unless you have a time. And notice it said at the point when t equals 0, because your velocity or your slope, your tangent equation is going to have t's in it. So you can't get a number for that unless you know the t that you're at. And the reason this is a good question, and the reason I left it in here is because remember, if you make it a unit vector, its length is now 1. Its length is 1. So you don't have long and short vectors. Now you just have length 1. And so what that tells you is just, oh yeah, that's the direction your acceleration is in, and that's the direction your velocity is in. So there's just kind of one more step to it, really, is all that's involved. So, awesome. I think we're good. Let's get you out of here closer to on time today. The review is up. So that's what I want to do tomorrow is just kind of look at that and make sure everybody's all aces on that. And as I said, we'll take the test Thursday. So stay after if you like, or I'll see you tomorrow.
Thanks, Doug.
Thank you all.
Nice thing.
I actually had a question.